Welcome to week 6 of CS395. This is Nihal speaking, and this week we are going to be talking about different exploit mitigation techniques. We're also going to be talking about one exploit mitigation in particular called ASLR, and we're going to be talking about ways that you can be getting around ASLR. So exploit mitigations are basically ways that security experts have come up with in order to make it more difficult to exploit a binary file. These include technologies such as DEP, Canaries, Pi, and ASLR. Because exploit mitigations are usually turned on in the real world, a lot of the exploits that we would have worked with so far wouldn't have worked in the real world because we turned off the exploit mitigation technologies. But in the next few weeks, we're going to be talking about how you can get around some of the more modern exploit mitigations out there, and what are some techniques that you can be using to still write your exploits even when these technologies are enabled. So these technologies do make exploitation a lot more difficult for us, but there are several methods that we can use to deal with each of these technologies that I'm about to go over right now. So the first one that we're going to be talking about today is called DEP, Data Execution Prevention. This basically marks certain regions of memory as either executable or non-executable. So there are two types of DEP. There's hardware enforced DEP, and you also have software enforced DEP. So with hardware enforced DEP, we're going to have something called a no execute bit, or NX bit for short. And every single page in the page table will have the NX bit. If the NX bit is set, then that means that that page cannot be executable. If the NX bit is not set, then the page can be executed. And so what that means for us is if we try to execute code in that page, the processor will just not allow us to execute code that is, if it's marked as non-executable. But if it is marked as executable, then we should be fine executing code on that page. For software enforced DEP, instead of working at the processor level, we're going to be working at the application level. And this is going to also make it more difficult to execute code in certain regions. The stack is almost always marked as non-executable whenever DEP is enabled. So this is going to make our lives a lot more difficult because now we can't just inject a payload onto the stack and then just have it execute on the stack. We need to make sure that if we're doing a buffer overflow, we have to make sure that we are executing code that is in an executable region of code. And the stack is not usually an executable region of code because in a normal program, there's no reason why you would push code on the stack. So this makes it more difficult for us to write our programs, or excuse me, for us to write our exploits. There's a technique called return-oriented programming that Sam is going to be going over next week. And this technique can actually allow us to defeat DEP. Basically, what this technique allows us to do is it allows us to selectively jump to segments in code that is marked as executable. And that will make sure that we are always going to be able to execute that code. So next technology is called stack canaries. Stack canaries are basically a random value that is going to be pushed onto the stack at the beginning of a function. So whenever you call a function that has stack canaries, that function will start off by inside of the near the function protocol. Right after it, it's going to push a random value onto the stack. Then at the very end of the function, we're going to pop that random value back from the stack, and we're going to check and make sure that it wasn't modified. If it was modified, then the function will immediately exit, the program will immediately stop, and if we were trying to do like a buffer overflow or something, recall that for a buffer overflow, we have to fill up we have to fill up things that are on the stack until we hit that return address. The stack canary will always come before the return address. So what's going to happen is when we try to do our buffer overflow, it's actually going to modify the stack canary, and it's then just going to exit the program immediately because the program's going to realize that the stack canary value was modified and that we're trying to do a buffer overflow. So to get around this, there are two methods. We can either leak memory off of the stack using something like a format string vulnerability, or we could try to brute force that value off of the stack and try to figure it out just by brute forcing it. Next, we have ASLR. So address space layout randomization is a technique used by operating systems. And what it will do is it will randomize the location of special areas of your code. So every time you run a program with ASLR enabled, you'll find out that your functions and your variables and whatever are going to be loaded at a different location. So this means that locations such as the base of the executable, which is, by the way, is where the executable is loaded up in memory. Also, your libraries, your heap, and your stack addresses are also going to be changed as well. And ASLR is going to make our memory addresses unpredictable. So that means that we can no longer use hard-coded addresses in our payloads if ASLR is enabled. Now, the problem here is pretty obvious. Whenever we did a stack buffer overflow, we would always rewrite the return address on the stack with our own return address, and we would just hard code that value. But now we can no longer do that. So we need to figure out a way to make an exploit work regardless of what the addresses are in our payloads. Next up, we have PI, Position Independent Executable. This is also known as Position Independent Code. And unlike ASLR, PI is more closely related to the instruction set in the processor. So ASLR is more related to the operating system, and PI is something that's done with the CPU. And a file that is a PI file is basically one that can execute at almost any address. So if you load that file up at address, let's say 0, it should be executed the exact same as if it was loaded at address, let's say hex 1000 or something. The way that a PI file works is instead of hard coding its addresses, it's going to reference data based on its distance from RIP or EIP. So if PI is not enabled, you would see an address like this, where the address right here is just hard-coded. But if PI is enabled, you would not see a hard-coded address. Instead, you would see a relative address, which is what you see right here, where we're addressing it based on what the value of RIP is. So sometimes in very poor implementations of ASLR, the addresses aren't going to be random. So like, for example, you might only have a byte or two that actually gets modified whenever the program is executed. There are other cases, like whenever you're dealing with a partial overwrite, that you might only have a few unknown bytes of the address that you need to overwrite or jump to. So in both of these cases, it is possible to just go through every single possible address and try to brute force it. Now, brute forcing becomes infeasible the bigger the address space is. And if it's properly randomized, then it's going to be very difficult to just brute force it, and it's going to take a very long time. Also, another thing to keep in mind, if you're trying to brute force, like, let's say a web server or something remote, brute forcing could also cause that program to crash. So a lot of times that's not something you want, especially if it's like a remote target or something that crashes before you get the right address. A much better way to defeat ASLR is to use something called memory leaks. So memory leaks, as I discussed in the format string lecture, basically we're going to leak out some memory from the stack, and we're going to see some address that's on the stack. Now, one thing to note about ASLR is your offsets will always be the same. So if you have like one variable or one function that's 32 bytes away from some other data or some other variable, it's always going to be 32 bytes away from that variable, no matter what. No matter how many times ASLR changes up the addresses, it's going to keep the offsets the exact same. It's not going to reorder anything or anything like that. It's just going to move around where the base of the executable is located. So what we can do is we could try to leak an offset off of the stack, and then we can calculate the offset of the thing that we care about so that we can jump to that thing. And this is very, very useful because we are now able to defeat ASLR without needing to brute force anything or do anything like that. We can just defeat it by leaking memory, and this will work almost all the time. So this week we are going to be exploiting the buffers binary. So if I just execute this binary real quick, it's going to ask us to enter in some input. So I'm just going to enter in a bunch of A's, and then it will print out those A's, and then it'll ask us to enter input for another buffer. So I'm going to enter in a bunch of B's, and then it just exits. So as you can guess from what it says right here, the very first buffer is vulnerable to a format string vulnerability. So I can print stuff off of the stack. The second buffer is vulnerable to a stack buffer overflow. So if I just give it in a bunch of input, you will see that after you give it a lot of input, it's eventually going to have a segmentation fault because we overwrote that return address. So the very first thing we're going to do for now is we are going to exploit this while ASLR is turned off. And then we are going to go back and turn ASLR back on again once we have been able to exploit it with ASLR turned off. So to look at what other security mitigations are enabled in this binary, we can use the rabin2 command, which is built into Kali. And we are going to use it with the -i specifier. And once we hit enter, it'll print out a lot of information about our file. If you look right here, it says canary false. So that means that stack canaries are not going to be on this binary. If we scroll down a little bit, it says NX false. So that means dep is not enabled on this binary either. And if we look right here, we have PIC is true. So that means pi is enabled on this binary. So those are the things that we have to consider when we're developing our exploit. And later on, we're also going to re-enable ASLR, and we'll have to deal with that as well. So the very first thing we have to do is we have to do a stack buffer overflow on the second input value. So what I'm going to do is I'm going to write this piece of Python code right here. What we're going to do is we're going to print out a new line first. So that's just going to ignore the very first input value that does the format string vulnerability. We're just going to ignore that one for now so that we can focus on the stack buffer overflow. Then when we go back and enable ASLR, the format string vulnerability is going to be more important then. Next, we're going to send it 232 bytes of A's followed by 8 B's. And what's going to happen is RIP, the saved RIP value is located 232 bytes into the buffer, the second buffer. And what's going to happen is the saved RIP value is going to be modified to be a bunch of B's. So just to prove that to you, I'm going to open this up into GDB. I'm going to run the program using the test file that I just created. Then I'm going to use info frame to print out information about the frame. And as you can see right here, the saved RIP value is a bunch of B's written in hex. So we know that we can overwrite the return address and make it to be whatever we want. So the very next thing that we have to do is we have to figure out what do we want to overwrite with the return address. And we want to make it so that it points to our shellcode. Since dep is disabled, we can just inject shellcode onto the stack, and we don't have to worry about any exploit mitigations like that. We will later have to worry about hard-coded addresses when ASLR is enabled, but for now, let's just ignore that and let's just use hard-coded addresses in our exploit. So we are going to disassemble main real quick. The very first part in main, right after the function prologue, you see that it's moving 0 into RBP minus something, and it does that a bunch of times. What's actually happening here is the program wants to zero out the buffers before it uses the buffers. So every single value in the buffer is going to be set to 0. So that's all it's doing right here. And we can just ignore the code right here because it's not really relevant for what we're trying to do today. The code that is relevant is down here. So we are going to set a breakpoint at maybe like right here, right after it's done executing all of this code right here that we care about. So let's just set a breakpoint at, let's say 368. So that's going to be this line of code right here. We'll put a breakpoint right there. And then we will run the program. So as you can see right here, our buffer is starting at this address right here, because that's where you see all of these A's being inputted. That's the start of our buffer. So I'm just going to copy that real quick. I'm just going to paste it in terminal just so that we have this address located somewhere. Next, we have to use our shellcode that we developed in week 2. So I'm going to go cd into the week 2 file. I'm going to do for I, and I'm going to do the for loop thing that we did earlier in week 2. But I'm going to use best shell. And notice that over here, I'm using these forward slashes followed by an X. Last time we just did a $i, which would just print out the exact hexadecimal bytes. But what we want is we want it formatted so that there is a forward slash, or yeah, /x right in front of the hexadecimal codes so that we can copy and paste it into Python. So I'm just going to do that by putting 4 slashes followed by the X. So next thing we want to do is actually, before we even make our exploit, we need to know the length of this right here. So let's just go into Python 3. We're going to say shellcode equals this thing, and then we just do length to get the length. And then we know that we have a buffer size of 232 bytes before we hit our return address. So I'm just going to do 232 minus 78 to get 154 bytes. So this number will be useful for us later, because actually it'll be useful for us right now because I'm about to develop the exploit right in front of you. So I'm going to use Python 3-c import sys.std out buffer.write. First thing we're going to do is we're just going to write a new line character so that it ignores the format string vulnerability buffer and just goes to the second buffer. Next, I'm going to create a NOP sled of, how much was it? 154 bytes. After that, I am going to input our shellcode right after that. So let me just grab it right here, copy that, paste it into here. And the last thing we need is our return address. So this is the address that we found earlier right here, this address right here. So we're just going to write that in little endian format. So this is 1, 2, 3, 4, 5, 6. We need 7, 8. Don't worry about the fact that we're using null bytes right here. I specifically programmed this so that it would read in null bytes. So don't worry about the fact that there are null bytes. Null bytes are not a bad character in this program right here. And we're just going to throw that into the test file. Okay, so once we do that, we are going to open up buffers inside of GDB, and we're just going to run it with the test file. And you'll notice that we will not get a shell right off the bat because this exploit will not work. So the reason it's not working is, let me just show you actually. If I set a breakpoint right at the return address, so let me just set a breakpoint right there, and then run the code, you can see that it is able to jump right into our NOP sled because this is our hard code address that we're going to be using since ASLR is disabled. So we can step right into there. But once, let me use this command right here. So what this command right here does is it examines 180 instructions starting at RIP. So when I hit enter, you'll be able to see 180 instructions starting from the current instruction, which is the NOP. So this right here is our shellcode. If I scroll up, you'll see like a bunch of NOPs right here because we did put a NOP sled at the beginning. But right here, you can see that we do have our shellcode. So I'm just going to set a breakpoint right here at the very start of our shellcode, just so that we can see what's going on, why our shellcode isn't working. Continue. So we have stepped into our shellcode right here. And so this first part, this is where we're closing stdin. And this second part is where we're reopening it. Now, this is where we're going to start having issues. What's happening is if we look at RSP is this value right here. And this is actually a value that's pointing towards our shellcode. So this is BFF8. Right now we're at DFBF, but we're very close to where this is pointing to. And what's going to happen is once we push enough stuff onto the stack, it's going to write stuff right. It's going to push stuff right onto where our shellcode is. So because RSP is pointing to a value that's on the stack, and because it's pointing to a value that's in our shellcode, it's writing on top of our shellcode. So this is a pretty easy fix. All we have to do is we have to manipulate RSP so that it is it's not going to modify our shellcode. And we just have to subtract a large enough value from RSP so that this doesn't happen. Maybe subtracting 300 will work probably. So let's go back into our desktop real quick. And I'm going to make a file called test.asm. And inside of this file, I just have 2 lines of code. I just say that this is the text section. And I just say that we are subtracting 300 from RSP. That's it. Save that, compile it, look at the object dump. And again, you will find null bytes here, but don't worry about the null bytes because I made sure that the null bytes were not bad characters for this binary right here. So you don't have to worry about them for now. So we are going to use that for loop trick again to obtain the bytes. So now that we are able to move or subtract 300 from RSP, if we just insert that at the very beginning of our shellcode, that should solve our issue. Just like that. But now our offset is going to be a little bit off, so it's no longer going to be 154. This right here was 1, 2, 3, 4, 5, 6, 7 bytes long. So if we just subtract 7 from 154, we get 147. So we just have to do that, hit enter. Next thing we're going to do is we're going to open buffers inside of GDB, and we're going to run it using the test, and now we should get a shell. So we have a working shell that works when ASLR is disabled, but this will not work outside of GDB. And the reason for that is because the addresses that GDB is using is different than the addresses that are being used outside of GDB. If I just show you real quick, it's not going to work. So the reason it's not going to work is because GDB offsets some of the addresses by a little bit. That's just something that GDB does for whatever reason. GDB has its own stuff that it likes to put at the beginning of the program, which offsets everything else. So to deal with this, we have to actually leak an address from the stack, and then use that leaked address to obtain an offset, and then use that offset for all of our hard-coded addresses instead. So what I mean by that is, first of all, this is also the same way that you can defeat ASLR. What we're going to do is we're going to open this up in GDB again. Since ASLR is currently disabled, we can just leak addresses from the stack, and we can figure out the offsets just based on these addresses right here. So the 4th address looks like it's very close to where our shellcode is located because our shellcode was at the same address, but with the 10, I believe. Let me just scroll up and check. Somewhere way up there. Right here. So it's just the exact same address, but instead of ending with 80, it ends with 10. So let's go back down here. So we know that the fourth address on the stack is x70 bytes away from the address that we care about, right? The address that we hard coded. So what we're going to do now is, by the way, we need to figure out how much is x70. So if we do x70, that's 112 bytes in decimal. So it's 112 bytes from what we care about. So what we're going to do is we're actually going to write an exploit script right now. And I'm just going to write this in Python. We need to use pwn tools for this script. So the very first thing we're going to do is we're going to open up the process. So that's just done using this command right here. And we're going to set stdin equal to pty. This will allow us to interact with a shell in case we get a shell. And we're just going to print out whatever we immediately receive. Next, we are going to leak an address from memory. More specifically, we're going to leak the fourth pointer from memory. So to do this, we're going to do p.sendLine, and we're just going to do %4 $P, and this is going to give us exactly the fourth value from the stack. And remember, this fourth value is going to be 112 bytes away from the stack address. So all we have to do to get the stack address is take the value that we received from here, subtract 112 from it, and that should give us our address. So to do this, we're going to say address equals, let's say, p.receive line. And we're just going to use strip because I'll add a new line character at the end, and strip will just get rid of that new line character. Next, we're going to make this an integer. And this right here, it says convert this into an integer that is currently in the base 16, because when we receive this, it's going to be as a string, but we want to convert that string into an integer. And right here, we indicate that it's going to be in base 16. Next, we are going to do address equals address minus 112 because we have to subtract 112 bytes from that address. Finally, we are going to convert this address into little endian format using T64. And this is the address that we can now use on our exploit. So we are now going to generate the payload. So our shellcode is going to be what I used earlier. Let me just check what it was. This right here. Copy that. Paste that right there. And it needs to be a byte string, so put that B in front. Next, we need to create our NOP sled. So that's just going to be x90 times, and this is going to be 232 minus the length of our shellcode, because we have exactly 232 bytes that we need to get to before we hit the return address. After we do that, we are going to submit we're going to create our payload. So our payload is just going to be the NOP sled plus our shellcode plus our address. And so this is our final payload that we're going to be sending to the process. So now let's trigger the buffer overflow. So we're going to send that payload over. And we'll use p.interactive to make sure that we can interact with that shell that we get. So just to recap, what we did is we opened up the process for using pwn tools. We leaked off the fourth pointer that was in memory. The fourth pointer in memory is 112 bytes away from the memory address that we care about the most. So we made sure that we subtracted 112 bytes from that memory address that we leaked. And now we're no longer using an hard-coded address. We are making sure that this works for pretty much any address that ASLR decides that it wants to put us on. After that, we're going to generate our shellcode just like before. But when we create our payload, we're going to use this address that we leaked off of this stack and subtracted 112 from, instead of using some hard-coded address. And then we finally just trigger the buffer overflow by using p.sendLine and p.interactive. So let's make this exploitable, and let's see what happens. So if we type in ls, who am I, we can see that it works. So our exploit works with ASLR disabled. Now let's exit, let's go back and make sure that we can use it while ASLR is enabled. You can see that it still works. So there you have it. That's how you can bypass ASLR. So just to recap what we were able to do, we were able to defeat ASLR by using a memory leak. What we did is we were able to leak an address off of the stack. We knew that address had an offset of 112 bytes away from the address that we cared about. It was 112 bytes away from the stack address that we wanted to jump to in order to execute our shellcode. So once we were able to leak that address, all we had to do was subtract our offset from that address, and we were able to exploit our program. So your homework, I want you guys to practice different techniques for defeating ASLR by yourself. I also want you guys to make sure you have an understanding for how you are able to defeat ASLR. Make sure you understand how today's exploit works. Also, you have a write-up due for assignment 3, and your write-up your exploit must work when ASLR is turned on in order to receive full credit for that write-up. All right, have a good day, guys.